Good morning, guys. 2nd of August, quite hot. So, we are on holiday. I won't be long. Just a quick demonstration of how the most useful things work. The fridge. Okay, this is the basic principle. Something to cool down here. A freezer just above, and then the heat that must be dispersed outside. Heat comes up from the food. It goes towards the cooling unit that usually is between the fridge and the freezer, and then heat is removed from the rear wall of the fridge. Also, the trick is that heat comes from the food to the refrigerating system at temperature between 0 and 4 degrees, while heat comes out from the refrigerating system to the environment at the temperature of about 50 degrees. This shift in temperature is achieved by the joint use of a compressor and a throttling valve. Now, most of house systems with the capacity below 300 liters use as refrigerating gas the R600. Okay, R600 is another name for isobutane. So let's start to do the model. When it comes to refrigerating application, the most commonly used systems are RefProp or PSLK. One of these two should. Check. Okay. Ah, the width of the dome on the x-axis is about 400 kilojoule per kilo. And here we are. Okay. The shape is the same. The critical point, according to Aspen Plus, is at about 36 bars. Okay, the critical point is right. The critical temperature is something as 135 Celsius. Okay, here we go. Now, Aspen Plus is able to reproduce the behavior of isobutane. Pretty thin. Now, how can one represent the Cooley cycle of the diamond? Well, suppose that we have a normal fridge that in the lower pressure part of the cycle works at an atmosphere. So, at this level. This means that the cooling power of the fridge is due to the gas that evaporates at this pressure. In case of isobutane, this pressure corresponds roughly to -12, -13 degrees Celsius. So it is a temperature low enough to make water freeze in the freezer. This line, drawn here, corresponds to what it happens here. This is where the gas evaporates after being liquefied. To accomplish this evaporation, the gas sucks heat from the food. After the gas is evaporated, it must be compressed. Now, at which pressure must the gas be compressed? Okay, the point is, after the compression, our isobutane will be cooled down in the rear wall of the fridge. This heat exchange takes place against air. In hot summer days, as today, the air outside can be as hot as 30 or 35 degrees. So, the temperature of the gas in the cooling coil must be higher than 30-35 degrees. Now, let's suppose that I compress the gas until 7 bars. 7 bars means a saturation temperature of 45 degrees. So I would have a delta T of 10 degrees against air. Supposing that my compression follows an isoentropic expansion, I bring it to 6 bars, more or less following this line. Now comes the cooling. In this kind of systems, the cooling brings the gas more or less to the ambient temperature. In this case, let's say 30 degrees in a very hot summer day. Now we are here. Now there is the expansion, the electrolytic one. In this kind of system, the expansion is not done in a turbine because a turbine is expensive. The standard house fridge has a simple and middle valve. This means an isoenthalpic pressure drop. Now you can notice that when the gas is expanded, it doesn't turn fully liquid. I mean, it remains at 0.25 or 0.27. This actually reduces the cooling power of the gas in the system. Nevertheless, in this kind of instruments, no more can be done, because to obtain a full liquid gas, you should go on with the refrigeration at least to -10 degrees. That is impractical. Now the question is, how much gas must be circulated in the system? This depends on how much cooling power we want to achieve. Now, standard household fridge, I mean, the ones with less than 300 or 205 liters of capacity, can freeze, let's say, 12 kilos of water in a day, half a kilo of water in an hour. This means roughly okay. So if half a kilo of water per hour is turned to ice in our fridge, then in an hour we must provide a cooling power of 170 kilojoule. This means 107 okay, 47 watts. How much isobutane have I got to run in the cycle to reach the cooling power of 47 watts? Or 170 kilojoule per hour. If the isobutane starts the refrigeration with a vapor fraction of, let's say, 0.27, the span on this axis is roughly 250 kilojoule per kilo. So 250 kilojoule per kilo compared to 170 kilojoule per hour makes up for 0.7 kilograms of isobutane per hour. Now we can start. Now, remember, we are here. 1 atmosphere, 0.27. Now I do the refrigeration. no pressure drop, full vaporization. Let's see what happened. Okay, 52 watt, pretty close to the 47 that we calculated before. Now, we have just done this step. Now the point is, we don't like feeding a compressor with a saturated bottom. Into a compressor, there should go always dry bubbles. So it is better to heat up this bubble a little and do the compression with the dried up bubble. So this step on the enthalpy axis can be done absorbing some heat okay, from the cooled isobutane before the frozen valve. Otherwise, this heat can be also released by the gas in this part of the cycle. Regardless. So for this simulation, we explore the second options. This is the cold feed. This is the cold product. Here I have my compression. This is entropic. This may be 0.8. We reserve something. Now, this is actually a recycle. Okay, but it will be solved pretty straightforward. Hot feed. Hot. Okay, I just want 3 degrees of solar heat. So we can see that in the first run, the system failed because at the very first run, before the heat exchanger actually works, there is vapor fed, there is a saturated vapor fed to the compressor. How can one fix this? We start in this way. We eliminate the error message. So now we actually see that the stream that goes into the compressor is fully vaporized. The outlet temperature is 52 degrees from the compressor. So we are more or less here. Now, how do we simulate this part of the system? Well, we start from the hypothesis that the cooling coil is just as long as to make the refrigerating gas achieve the same temperature of the outlet air. So we have a very, very large heat exchange surface. In this case, we can neglect true heat exchanges problem and just do like this. I assume that the coil can equalize the temperature of the gas with that of the outer air, 30 degrees in the summer. This passage is done while still on the high pressure level. I am running this way. Then, after the coil, I do the throttling. Okay. As you can see, the vapor fraction matches. So we are just ready to close the cycle. I remove this. I reconnect S1, I define S1 as my tier string, and I go on. Okay, the flow sheet is already loaded. I am giving a cooling power of 52 watts. That means 52 3600 24. Okay, 4500 kilojoule in a day. This means that in a day I can freeze 13 kilos of water. That is just the maximum cooling capability of a 200, 180 liters fridge. And this is due at the expenses of 16 watt of electric power consumed. 16 watt, it means 58 kilowatt. 58 kilowatt hour. Okay, guys, this was a advertisement. We are on holiday, just to relax and see how your fridge is working in this moment. Okay, see you next time with the next video. I guess that something will come up in September. Nice holidays.